Hey guys, so I just wanted to show you the agenda to start here. So we are going to go through the 4.1 and 4.5 modeling notes together. And then starting on Friday, you'll have a work day, and then we will be reviewing for our test that's coming up next week. So let's take a look at the calendar real quick. So if you notice here, we are on the 19th. Starting Friday, like I said, is a work day, and then we will be reviewing Monday, Tuesday as well. And then your unit test will be on your block day. So I have made a printout for these notes, so go ahead and make sure you grab those before we get started. We're actually going to go through day 1 and day 2 of exponential modeling. So every time there's a teamwork, I'd like for you to pause the video and with a partner or with yourself, try out the problem on your own before you go through it with me. So take a second, read this teamwork, and go ahead and answer questions A and B. So if you go through this problem and you're trying to determine how much money you have after 5 years if you started with 10,000, we don't technically know any formulas yet. One potential way that you could have solved this would have been thinking about each year individually and what would have happened. So if I think about my years and I say in year 1, I started with $10,000 and I had a percentage rate of 2.75%, which transfers to 0.0275 as a decimal. And that gives me about $275. That means I would take this $275 and I would add it to what I started with after year 1. So in year 2, I'm now starting with $10,275. That year, it multiplies by 0.0275, and I would get roughly 282.6. I would add that value to my starting value for year 2, which was 10,275. So that gives me 10,557.6. Multiply that by 0.0275, and I get approximately 290.3, and continue that on down until year 5. And for year 5, that would give me a total of about $11,452.70. So in 5 years, with a 2.75% rate of increase, I would have grown my $10,000 to $11,452.70. Okay, let's look at part B. Part B says, by what percent did your initial investment increase? Well, if I grew to $11,452.70, I could divide that by 10,000, and that would give me approximately 1.145, which means this is my rate of increase. So I could say about 14.5% increase. Okay, moving on to the next piece, you should see your formulas for compound interest and simple growth or decay. So take a minute to read through these. You've actually seen them before, and these are the formulas that we can use to calculate a problem like we just did in the teamwork in a much quicker way than doing each year individually by hand. Okay, so that's what we're going to do, looking at these 4 problems. So it says verify your answer from the teamwork using the formula. Okay, so really we could use our compounding period. So if you go through the compound interest, A is what you have at the end, okay, over a certain amount of years. P is your starting point. R is your rate, turning your percentage rate into a decimal. P is your time, and N is the number of times compounded annually. Okay, so that means annually would be 1 time a year, quarterly would be 4 times a year, and so on. Continuous compounding, you use A equals PE to the RT. That has E in the formula. And then simple growth or decay, similar to when you compound annually 1 time a year. So really for that first one, we could use either formula. I'm going to go ahead and use compound interest. So we will say A equals 10,000 times 1 plus our percentage rate, which is 0.0275, because I'm working from the teamwork problem, divided by the number of times compounded, which is just 1 time, and then raised to the NT, so that's going to be 5.1. Okay, when I plug that in my calculator, you're actually going to get approximately $11,452.73. And if you compare to what we got when we did this by hand, that is pretty close. Okay. So moving to the right side, it says how much more would you make if you were compounded quarterly? So compounded quarterly means we're going to compound 4 times, right? So it's going to be the same formula, A equals 10,000 times 1 plus 0.0275, now divided by 4 times, and then it's 5 times 4. When you plug that into your calculator, you should get approximately $11,468.62. Okay, but that doesn't answer our question because it says how much more. So what I need to do is I need to take this $11,468.62 and subtract my $11,452.70. And that will give me approximately $15.89. So that's how much more I would make if I compounded quarterly. Be sure to pause the video at any point in time that you need to, or if you'd like to challenge yourself and try the problem first before I work through it. Now for every second. So first we have to figure out, we're compounding annually, so that's per year. So we need to figure out how many seconds are there in a year. So if we think about that, there are 365 days. There's 24 hours in a day, 60 minutes, and 60 seconds. So if we multiply all that together, we're going to get 3, 1, 5, 3, 6, and 3 zeros, which transfers to 31,536,000 seconds per year. So that's what we are going to use. So plugging into the formula, I'm going to have A equals 10,000 times 1 plus 0.0275 over that large number, 3163 raised to this power multiplied by 5. And when you plug that into your calculator, you should get approximately $11,473.98. Now, if you look at compounding continuously, this is when you use that formula A equals B to the RT. So let's plug in there. So we are going to have A equals our principal amount is 10,000 still. E is part of the formula. Our rate was 0.0275. And then our time, which is still 5. When you plug that into the calculator, and don't forget your E is above your division sign on your calculator, so hit the second button, hit the division sign, you get approximately $11,470.02. Look at these two. They're so close. Okay, so compounding every second and then compounding continuously pretty much is the same. Okay, moving on, we're going to end this day 1 with a teamwork. So take a second to pause the video and try this out with your partner. So I went ahead and labeled what I had and plugged it into my formula. Okay, so take a second to double check yours. What you need to recognize here is when you're solving for the exponent, that should trigger for you that we are going to solve using logs, and you can use common log or natural log. So what I'm going to do first is I'm going to try to isolate this piece that has the exponent. So I'm going to divide both sides by 1200. So when I do that, 2400 divided by 1200 gives me 2 equals, when I add these two together, I'm going to get 1.023 because 0.023 divided by 1 is 0.023 raised to the t power. To bring the power down to a leading coefficient, I'm going to have to take the log of both sides. I'm going to take the natural log of 2, bring down that t, and take the natural log of 1.023. To get t alone, you're going to divide by the natural log of 1.023. That cancels because I divided, and that is going to give me t, right? So approximately, when I plug this into my calculator, you're going to get t to approximately be 30.5. So what that means is going to be about 30.5 years. Well, if we transfer that to our months, that's going to be about 30 years, and a half year would be 6 months. And now we're going to move on to day 2. So again, pause this video to attempt the teamwork with your partner. Quick reminder on number 1, we've already done this. It's just recapping the skill of storing something. So remember, you're going to type this into your calculator. Then you're going to hit that STO with the arrow button and then choose alpha, A, or whatever letter you'd like. And then you'll go ahead and show your check. So here's the worked out teamwork. So take a moment, check over your answers, and we're going to go ahead and move on. Next, we're looking at one more equation, and this is why we love mathematicians, because this equation works for both growth and decay situations. So what I need you to recognize is that this A sub O, it looks extremely similar to the PE to the RT. It's actually not going to be any different because I can use any variable I want to be able to represent something. If I wanted to plug in a Z, I could do that if I wanted to, as long as it's defined. Okay, so let's go ahead and move on to our first example. So these are going to be problems which were given an equation, and we're just going to answer a question. So given this model, it says, what is the original value being measured? So our starting principal value. It's going to be here, 200.3. Part B says, is the model representing growth or decay? So what we want to look at with a value that has E in it, we want to look at our exponent and look at that 0.052. That is greater than 0. So that means it's going to be a growth function. Okay, and then it says at what rate is the total growing or decaying? So we are growing, and since it's 0.052, that actually is going to transfer to about 5.2. Okay, so breaking down an equation that's given. If you move on to the second one, it says the population of our nation is on the rise. Read through that. It says in 1970, we had a 203.3 million population, and in 2010, we had a population of 308.7. Should this be growth or decay? We're going to say that this is going to be growth. How do we know? Because it says that it's grown. So this is going from 203.3 all the way to 308.7 million. Using what we have, what is the growth rate? This problem, since we started in 1970, that's going to be considered our time zero. And since we knew that it grew to 2010 to 308.7 million, I subtracted that to find that our time frame was 40 years between those two values. And then I'm going to use this equation and plug in. So really what I have for my ending value is 308.7 equals to my starting value of 203.3 e to the k, which is what I don't know, times my time, which is 40. So take a moment, pause the video, and try to solve this equation using logs. So check your work with mine. You isolate the piece with the exponent, take the log of both sides to solve for k. You get 0.01. So moving on to C, we're going to use that for the growth model of this situation. So that means I'm going to write a model, an equation for this context. So it's going to be A equals, and since 1970 is my starting point, 203.3, which was the population, will be my principal value. E to the 0.01t, that is the value, equation that we can plug into. Okay, so we're going to use that. It says, by which year will the U.S. population reach 335 million? So what we're actually going to do is we need to figure out, okay, reaching 335 million, we need to plug that into this model. So plugging into this model, we are going to look like 335 equals 203.3e to the 0.01t, and we are actually going to solve for the amount of time. So pause the video and take a second to pause this equation using logs. To solve this equation using logs, sorry. When you solve this, you isolate the piece with the exponent to get t to be approximately 49.9, which is about approximately 50 years. So if I add 1970 plus those 50 years, I'm going to get approximately 2020. So that's when that should happen. Part E says, what should the population be this year? Well, lucky for us, our year is 2020 this year. So that means we should get approximately 335 million. So what I would like you to do is just go through, plug in, and solve for this year of 2020. So what that is going to look like is going to be into your model. T is equal to 50. So you're going to have A equals 203.01 times 50. And actually, when you plug that in, you're actually going to get 335.19 million, which is approximately what it says. Real quick before this video runs out, I forgot to point out an error in here. In the simple growth or decay, this should be greater than 0 or less than 0, like I stated in the example. Okay, so great job. You have a worksheet to work on and then a full work day on Friday. So I will see you guys then. Have a great day.